Swayam Prabha. Digital India. Educated India.
So, welcome to a new topic and a new module in our course here, and we are going to spend the next week or so looking at this area of planning, or as we sometimes say, domain independent planning. And essentially planning is a task of something that we have addressed earlier, that we had classified search problems as two kinds. One was a planning problem and the other was a configuration problem. So, in a way we are coming back to the planning problem, and we are going to focus only on planning problems and study what has been happening in this field. So, as I said, in the last 20 odd years a whole community has emerged to work on planning, and they have their own conference, they have their own competitions, and a lot of work has been going on in this area essentially. Partly this work has been motivated by the fact that people have started building autonomous systems, systems which will take decisions on behalf of their owners or users. They will perceive the environment, they will have goals to achieve, and they would have to decide by themselves as to what are the actions that they need to pick to achieve those goals. So, this is broadly speaking what happens in the world of planning. There have been some very impressive examples where planning has been used, and one of them has been in the area of space exploration. So, quite a long time ago there was a experiment called Deep Space 1, in which they deliberately introduced some faults in a spacecraft, and then they wanted to see whether the spacecraft can monitor, detect and plan its activity in the light of this deliberately introduced defect. Another example from the space domain has been space exploration. So, for example, NASA had sent Mars rovers about 15 odd years ago, and the distance from Mars to Earth is so significant that it takes light, which would be the carrier for a signal, to many minutes to reach the Earth. Not only that, so that means obviously you cannot remote control a robot from Earth, because by the time you send a signal, say turn left, the robot would have gone straight and fallen over a cliff or something like that. So, clearly it needs to be autonomous, and not only because of the time lag between Earth and the Mars, that the time it takes for the signal to achieve, but also because at times a spacecraft might be out of signal zone, it may be on the other side of Mars and you may not be able to even signal or receive a signal. There have been similar applications closer to Earth. Specifically, I remember for example, the Indian Space Research Organization was looking at the possibility of introducing autonomy into its low Earth satellites. So, satellites which are visible to a ground station only for 20 minutes in a day or maybe a bit more than that, and otherwise they are orbiting the Earth and you cannot communicate with them. Of course, you can communicate with them if you have ground stations in other places. So, India has had ground stations in other countries, but the lure of having autonomous satellites is quite there, and especially if you want to do things like remote sensing and all, you have to manage when to take images, when to upload images, when to download images, whatever the case may be, and planning again has been useful in that. Nowadays, of course, that autonomous vehicles do a fair amount of planning. They do mostly route planning, but nevertheless it is a planning activity. They also have to plan when to accelerate, when to decelerate, when to stop, all that is part of deciding what actions to do. And obviously, there is a world of robotics in which you want to have autonomous robots which are doing things for you. So, they amongst other things will need to be able to plan. So, for these many reasons, planning has emerged as a active area of research, and what we are going to do is to look at the basics in this next week or maybe 2 weeks, and look at what are the kind of algorithms that have been developed. So, one thing that we will start with is that we will change our perspective of problem solving. So far what we have said is that our perspective of problem solving using search has been state centered. So, we have said that we have a set of states and you have a move gen which allows you to move from one state to another, and we have been deliberately vague about what this move gen function looks like. We have also been vague about how the representation of states is done. So, our focus has been on the fact that given that there is a move gen function and given that there is a space to search, what are the best strategies for searching through that space. So, in this state centric approach of things, the solution that we found also was a sequence of states. So, we said that the path of found by an algorithm, for example, like A star is the sequence of nodes that it goes through essentially. Even when we talked about solution space search, for example, when we talked about TSP, the solution was still expressed in terms of states. For example, we said that this is a candidate tour and you can alter this tour or you can extend this tour, partial tour and things like that, and everything was centered around states. The planning community takes a different viewpoint. They say that we want to talk about actions and we want to look at an action centric view of problem solving. Even when we plan in the state space, we are going to talk about actions. So, solutions in the planning community are expressed as sequences of actions rather than as sequences of states. Obviously, actions will be applicable in some states. So, we will have to consider as to when they can be applied, and they may be relevant to goal states, because our task is to achieve some kind of a goal state or a goal description. And we will also look at a little bit an area of which is called plan space planning or partial order planning, in which we do not even represent states. The space that we search through is entirely that of plans essentially. Now, in our study so far, we have on and off introduced the notion of actions. In particular, if you remember, when we talked about the 8 puzzle kind of a problem, we said that actions can be named as left, right, down or up, which we call as LDRU, and we kind of talked a little bit about it at that. This is that you have to choose between those actions, but that was only in some sense adding to the basic search mechanism, which was state based essentially, that you had a move gen function which gave you a set of neighboring states and you have to choose one of them. Now, we want to consider a viewpoint where we take an action centric view, and even if we are talking of state space planning, as we will start by doing, we will still consider that in a given state what are the actions that we can apply and then choose between those actions. So, let us get on with this thing. There have been a couple of books by Malik Galab and Dana Now and Traverso, for example. They have written a very popular book on automated planning, and more recently they have come up with a book which is called Planning and Acting, in which they focus also on how to monitor the actions that you are doing and what do you expect of actions and how do you verify whether those expectations are met or not. And they gave us this kind of a definition or a slogan, you might say, that planning is the reasoning side of acting, that an autonomous agent has to act in some world, but before acting the autonomous agent has to deliberate, essentially decide as to what are the actions that it should do. This is different from what we can call as reactive systems, which simply sense and react in some predetermined kind of a way. When we talk about planning, we have goals in mind and we have an explicit process of reasoning or deliberation that we expect the agent to do. So, an autonomous agent in some domain would have certain goals to, and that is either given to it by some kind of a user or a manager, or it may derive goals of its own if it is a truly autonomous agent. Then its planning has to be done in terms of a repository of actions or operators that are accessible to it. So, a planner will have certain set of actions available to it, and we will see how they are described. It could use any method. In particular, we will focus on search for the moment, but in general it could be other methods as well, and the task would be to find something called a plan. So, a plan would be like a first class object in programming terms, something which can be passed around and manipulated and things like that. And obviously, the agent will have to execute and monitor the plan as well. Now, this goal driven behavior of agent, in the sense that the agent has certain goals to achieve and is deliberating how to achieve those goals, can be seen as a cycle of 3 steps. First, you perceive what is the environment, what is true in the environment, and in terms of what is the given state and so on. Then you deliberate as to how do you do something that would move you towards closer to your goal, and the third is that having chosen the action, you need to actually act in the world, which means you will actually change the environment. You will, for example, move a chair around or whatever, put some clothes out to dry in the sun, whatever the actions are, you have to actually do them. Then again see what the new world is like and what you need to do in terms of the original goals that you have, and again continue deliberation. So, it may happen that deliberation may happen once and for all, and then you simply execute the whole plan, but it could also happen in some situations where the world is not entirely in your control and you have to keep monitoring and perhaps replanning as you go along essentially. For example, if you are planning a trip to the mountains and you are going along a particular path, and for example, in Himachal, and then you see that this road that you wanted to take has had a landslide and there may be a delay of 4 hours or something like that. Then you have to replan. Should you wait there for 4 hours and maybe have a meal or something, or should you backtrack and try a different path? So, in the real world, everything is not in your control and you may have to monitor and maybe replan and so on. But the basic cycle of a planner is perceive, deliberate, act, or sense, deliberate, act essentially. So, we can model, we can think of planning as follows. Our view of planning is going to be domain independent, okay, in the sense that we will not say that we are writing a program to solve, for example, the 8 puzzle or the Rubik's cube, or let us say the missionaries and cannibals problem, or whatever the case may be, in the spirit of what we have been doing in AI, that we will write general purpose algorithms and we will expect that somebody will give us what we said so far was that somebody will give us a move gen function and somebody would give us a goal test function and maybe somebody would give us a heuristic function. Now, we are saying, or we are going to say, as you will see, that we have a well defined way of describing a domain and we would expect a user to describe the domain in the language that we will specify. These languages are called planning domain description languages, and we will kind of have a passing look at them as we go along. But the idea of planning, the research in planning is largely domain independent, and it says that given a set of planning operators accessible to a agent described in the language that we are talking about, given a start state which is also described in the language that we are going to soon discuss, and a goal description also expressed in the same language, what is the sequence of actions that I would construct to achieve the goal that has been given to us. Now, you can see that there is a domain here and there is an agent which is kind of anthropomorphized here, looking like a human being, and this agent is the one which is acting in the world. The agent can perceive what is happening in the domain and the agent can act upon the domain. So, this perceive and act are the two parts that we have been talking about. We said perceive, deliberate and act. Deliberation we have not shown here, and that is what we are going to study essentially. Now, I have drawn in this figure the agent as somehow being outside the domain, but that is only for the case of a schematic diagram. In practice, of course, the agent would be in the domain. For example, if there is a robot moving around things on a shop floor, then the robot would be in the domain itself essentially, but it is just for the case of drawing a neat diagram essentially. The agent of course will have objectives or goals to achieve, and deliberation is oriented towards achieving those goals. Either the agent is acting solo by itself, or there may be other events which are happening essentially. So, other events could be, for example, there may be other agents also, or it could be events happening in nature, or what we sometimes call as exogenous events. For example, rain may suddenly fall or something like that, and that may also change the domain. So, the domain is manipulated either by the agent or by other agencies, but for our case we will confine ourselves to the case where the agent is the master of the world and the only one who can make changes in the domain. So, those are the simplest kind of planning domains. So, this is what planning is about, and a planner can perceive the world and it produces actions designed to achieve its objectives or goals. Then in a static domain, the agent is the only one who acts, there is nobody else which can change the world, and in a dynamic domain we can have other agencies like other agents or nature, for example, or for example, market rules as to the market opens let us say at 10 in the morning and closes at 7 in the evening, or whatever the rules of that particular city might be. If you want to go shopping somewhere, you have to be aware of the fact when will the shop be open essentially, and those whether the shop is open or closed is not within your control, but somebody else or some other agency is doing that. Let us look at these different aspects one by one. First is the perception. We have said that an agent can perceive the world essentially. Now, perception may or may not be complete, it can be modeled. Domains in general can be modeled with various degrees of expressivity, and one of the parameters is going to be how much can the agent see the world essentially. Now, for example, if you treat let us say playing a game of chess like a planning problem, then from the planning perspective that you are deciding your moves, you can see the entire chessboard and you can see where the pieces are, what are the moves possible for you, what are the moves possible for your opponent, and everything is known to you, and that is why we call such a situation as a complete information game essentially. Likewise, a domain may be complete information or it may be with partial information. So, in the simplest domains the agent can perceive the world perfectly essentially, but of course, such domains are rare, but they are good for the purpose of study, and it has been shown by a group of researchers, Gupta and now, more than 20 years ago, that even in the simplest of domains that we are going to be talking about, planning is the planning problem is a hard problem. It is a problem which is called in the class of complexity called P space, which basically says that it may take exponential time and polynomial space essentially. So, it is a hard problem to solve, and that is why we would begin our baby steps with the simplest of domains, and in the simplest of domains the agent can see the world perfectly. Now, obviously, in the real world you cannot do that. If you, for example, are staying in your college campus or in your home in a city, and you want to, let us say, go to the train station, your plan may be that you would go out and catch a bus at some point to the station essentially. But of course, you do not know what is happening in the world out there. For example, you do not know whether it is raining or not, you do not know whether there are traffic jams, you do not know whether there is a bus strike, all kinds of things could happen essentially. And yet you have to somehow plan in the face of this uncertainty, but that is a little bit too much for us at this moment. And we will assume that the domains that we are working on are simplest, and in which the agent can see the world perfectly. The agent knows exactly what is true in the world and what is not true in the world. So, such domains are called complete information domains. As I said, in realistic situations, the agent may have only partial information. You may not know whether the particular, for example, you may be going to a movie theater and you may not know whether tickets are available or not. Of course, in the modern age, you can always do all this stuff online, but assuming that you are in a small town in a remote part of the country, and that particular theater owner has not created an online system, then you have to work with the partial information. You have to go to the theater and hope that you will get a ticket essentially. Or if you are traveling to, let us say, traveling to a train station in a bus or an auto, you do not know whether there is going to be a traffic congestion and whether you will reach on time and things like that. And again, you have to work with partial information. But we, as I have been saying, will stick to simple domains. Now, what about the goals of the agent or goals of the objective? What kind of goals that we will give to our agent to achieve? They can also be vary in degrees of expressivity. The simplest, and that is what we will assume, is satisfaction goals on the end state. By this we mean that we will specify certain conditions and which should be true in the end state, and all of those conditions have to be achieved for you to say that the plan has worked or the plan is successful or the plan is a valid plan. So, I might say that this should be true, this should be true, and this should be true. For example, I should have bought a toothpaste and I should have bought a book and I should have eaten in the restaurant by the time I finished my activity, then all of those should have been done essentially. On the other hand, you may have soft constraints on the end state. We say, okay, these are the things that you want to do. You want to buy a toothpaste, you want to buy a book, you want to eat in a restaurant, you want to take a stroll on the beach, and you would like to, if time allows you, to go and buy some other groceries that you need for your home. You may have many of these goals, and yet all of those goals may not be feasible. Time may be limited. The shops may be open for only a short period of time. In such situations, we can model the planning problem as a problem of soft constraints, in which we say that achieve as many goals as you can, and then we evaluate the plan based on how many goals have been achieved. So, for every example that you cannot achieve, you can impose a penalty on the plan, and then the task becomes a task of optimization to say that I want a plan which has the least number of penalties essentially. The previous case, where the goals are only satisfaction goals, the task is a satisfaction task. Either the goals have been achieved or they have not been achieved. So, either the plan is successful or it is not successful. Whereas, for soft constraints, you can have degrees of success and say that, okay, the plan is completely successful or partially successful and things like that. But then obviously, optimization is a harder problem than satisfaction, and algorithms which try to plan with soft constraints are more complex than that. Then why should we have only constraints only on the end state? We may have constraints on the trajectory also. So, you might say, for example, in Chennai, if you are going, let us say, from IIT Madras to the central station, you might say, I want to go along a path from which I can get a good view of the sea. Now, this is not part of the end goal. End goal is you have to be at the central station, maybe at a particular point of time. The trajectory constraint says that I would like a trajectory to be of a certain nature essentially. Or for example, if you are transporting a patient from one city to another, then you may have trajectory constraints that choose a path in which at all points of time I am within 20 kilometers of a hospital, or I am within maybe 20 kilometers of a petrol pump essentially. So, that you are sure that if you have to revise your plan, you would be in a situation where you can revise it, because if suddenly there is an emergency and you have to take the patient into an emergency ward, there must be a hospital to start with essentially. Okay. So, you may impose a constraint that find me a path from city A to B, but in such a way that I am never too far from a hospital essentially. So, we have constraints on the paths too, and these are called as trajectory constraints. Again, trajectory constraints may be hard or soft, that you may prefer that certain things are met, but if they are not met, then you may be willing to live with it essentially. Now, let us talk about what the agent can do. What are the kind of actions that agent can do, and there is a whole variety of them that we can think of. The simplest is that actions are always deterministic, that they always achieve the intended result essentially. So, for example, if I have a pen lying on the table and I plan to say pick up the pen like this, then when I execute the plan, I am holding the pen. So, it has achieved the intended consequence of the action. On the other hand, there may be actions which are stochastic, which may or may not achieve the intended results essentially. So, for example, if I for example were to go and try to play basketball, and then I would say, okay, here is an action I am doing, I am throwing the ball into the basket and I may chuck the ball towards the basket, but as you can probably guess, the ball may or may not go into the basket. So, such actions are called stochastic actions, where you intend to do something, but that may or may not happen essentially. So, it could happen, for example, if you are trekking in the mountains and you are walking on a glacier, which is a kind of an inclined surface of hard snow, you may want to say that I am going to take 5 steps in the forward direction, but you might find that yourself that you have slipped down and fallen a little bit on the wayside essentially. So, the world of course is always full of stochastic actions. We will assume that actions are deterministic, that if you say pick up a pen, then at the end of that action the pen would be picked up. If you say take 5 steps in the direction of the door, then by the time those 5 steps have been taken, you are that much closer to the door. Then actions can have duration normally. In the real world, actions are never instantaneous. In the real world, nothing is instantaneous, because there is energy involved. But in the simplest of domains, we will assume that actions are instantaneous and there is no notion of time essentially, which means that if I say pick up a pen, it happens at time t1 essentially. We can model time as a discrete sequence. At t1 I can pick up the pen, at t2 I can give it to a friend, at t3 the friend can start writing with the pen. All these things are modeled as happening instantaneously, and the goal is to find the correct sequence of actions. We are interested in the sequence of actions, we are not talking about time at all, even though in the real world we may often do that essentially. So, again if you are doing route finding, for example, you might say go from location A to location B, then location B to location C and so on, without worrying about time, in which case you are simply trying to find a path essentially. When you talk about optimal paths, it is a different matter. On the other hand, actions may be durative, they may have a starting time or an ending time. So, for example, if you want to make a cup of tea, you might say take a pan, fill it with water, keep it on the stove, light the stove, wait for the water to start boiling, add the tea leaves, close it for a few minutes and then strain it out. Each of these actions has duration. It is not as if you can boil the water in 1 minute, one instant or something like that. It takes a certain amount of time, and there have been domain descriptions where people have worked with durative actions, which take time essentially. That is particularly important if you are talking about situations where you can do many actions in parallel. So, typically if you see the way cooking happens in an Indian household, people have gas stoves, most people have gas stoves, and they have 2 or 3 burners on them, and something is going on one burner, maybe some dal is being cooked, and on the other burner you may be stir frying some vegetable, and these things happen in concurrently, but they may take each may take a different amount of time. So, for example, the dal may take 20 minutes or 30 minutes to cook, and if you are stir frying, then you may be in the last stages and you may finish in 5 minutes, and then you may start making chapatis, and each chapati may take 2 or 3 minutes to make. So, durations count essentially. If you want to finally say that okay, I want to prepare my meal as quickly as possible, and I am allowed to do concurrent actions, then planning becomes a much harder problem. We will stick to deterministic instantaneous actions in our study here. Finally, actions may have associated cost, and then you may worry about what is the cost of the plan that you have found. We may start off, or we will rather confine ourselves only to the simplest of costs, which is the number of actions that you have to do, and we would say that shortest plan is the one in which the number of actions is the smallest. So, I said that in static domains, agent is the only one who is acting, and so you can entirely predict what the domain will be like after you have done, let us say 6 actions or 10 actions, but in a dynamic domain that may not be the case. In the static domain, the planning agent is the only one that makes changes. In a dynamic domain, there may be extraneous events, for example, there may be rain, or the shop may be open or the shop may be closed, and things like that essentially. There may be other agents. So, we often model agents and nature in some sense in a different way. One could think of nature as some huge agent, but when we talk about agents, we in some sense say that let us say there are 2 robots and 3 robots or whatever, 2 people or 3 people, and if you have to move, for example, a cot from one room to another, then the 2 robots have to work in a coordinated fashion, so that both of them should plan their actions, so that both of them lift the cot at the same time. All these kind of situations can happen in multi-agent situations. So, you may have agents which are collaborating agents, or they may be agents who are adversarial agents who are trying to stop you from achieving your goals, or they may be agents who are competing with you for common resources essentially. So, for example, you are standing in line to buy a ticket, and there may be other agents also standing in line to buy tickets for themselves, and of course, as happens in India, lines are never well formed. So, they are competing, and you may have to kind of be careful not to let them barge into your line, all that kind of stuff essentially. The simplest kind of domains that we are going to be dealing with are called strips domains, and these are the oldest planning formal systems that were devised, and many people say that STRIP stands for Stanford Research Institute Planning System, and it was a planning system which was devised for one of the earliest robots called Shaky, which apparently roamed the corridors of Stanford at that time. And the strips domains are the simplest, their actions are instantaneous, and all these things that we said. The domain is finite, static, completely observable environment. The set of states and the set of actions is finite. Changes occur only in response to the actions of the agent. They are static. Agent has complete information, you can completely see the world, and there are no other agents. Then the goals are hard constraints on the final state. We do not bother about what happens during the plan, and they have to be achieved to form a valid plan. Actions are instantaneous, there is no notion of time, and we just want to find a sequence of actions that will achieve the goal. Actions are deterministic in the sense that what we plan will happen essentially, no accidents, no execution errors. and no stochastic effects. We are not talking about, for example, rolling a die in a game of backgammon or snakes and ladders and hoping that you will get a 5 or something like that, may or may not happen. Such simple systems can be modeled as state transition systems, which can be defined as a triple of a set of states, a set of actions, and a transition function essentially. So, S is a finite set of states which the systems may be, and the system moves from state to state. It is like a finite state machine. A is a finite set of actions that the actor may perform, and of course, certain actions may be performed in certain states and all that kind of stuff, we will see shortly. And there is a transition function, let us call it gamma, which takes a state and takes an action that you do in the state. So, you take a state and you do an action in the state, and it results in the system or the agent going into a new state essentially. So, it is a partial function called the state transition function. If the action A is applicable in the state S, then gamma S A is the resulting state essentially. I have said that there has been a considerable amount of work in the last 20-30 years in the domain of planning, and people have devised a sequence of or series of languages which have been all called as planning domain description languages. These are languages in which any user can specify a domain, specify the predicates in the domain, specify the operators in the domain, and specify a planning problem in the domain, which means that you specify the start state, the goal description, and the set of operators available to you. One thing that has been happening in the world of planning, in the planning conferences, is that every time there is a conference, they also have competitions. So, they say, okay, our domain will have these kind of characteristics, you write a planner and we will see whose planner does the best essentially. So, starting with a set of languages, which was the strips like language that we have just mentioned, there have been a sequence of new languages which are more expressive as you go along. The idea is that the researchers working in planning algorithms can use these standardized representations, which basically means that if two different groups, research groups are writing planners for a particular domain, let us say a robot sorting out things in a shop floor, they do not have to devise their own representations, they will work with the standardized representations, and then they will also be able to compare their algorithms performance essentially. So, components of a PDDL planning task are as follows. You have to describe what are the objects in the domain that the planner has to work with. You have to describe the predicates that talk about the properties of the objects that we are interested in. We have to describe what is the initial state that the world is in. We have to describe the goal specification as to what do we want to achieve, and we have to say what are the actions or the operators that are available to the planner or to the agent for changing the world. So, if you describe all these things, you have described the domain in a planning domain description language essentially. So, as I said, there has been a family of languages. Let us quickly run through them, and we will see that the simplest was PDDL, which was essentially the strips domain that we spoke about. The next language introduced something called conditional effects, PDDL 1.2. Conditional effects basically say that the effects of an action would be conditionally true essentially. So, for example, if I am sitting in my office and I take a book and put it in my backpack, and then I go home, then is the book at home or not? Now, the book could be at home if I go home, provided that it was in the backpack where I put it. So, my action of going home would also transport the book to home, provided the book was in the backpack. If the book I have forgot to put it in the backpack, then the same action would not achieve the effect of taking that book home. So, such actions are called conditional effects. Then in 2.1 we introduced numerical fluents for, so for example, how to model how much fuel do you have in your let us say car or whatever you are driving, so that you can plan your trip accordingly, and maybe plan at some point you would go to refuel your vehicle. You can have plan metrics which will say how much fuel you have spent, how much has it costed you, and that kind of stuff. They also introduced durative actions. We have spoken about them, that actions which have a start time and an end time. Then in PDDL 2.2 we had derived predicates. So, derived predicates basically say that if something is true, then something else is also going to be true as a consequence of that essentially. So, if you achieve something, then you may also end up achieving something else which is directly related to that. So, in the sense that the derived predicate do not have to be explicitly planned for. If you plan to achieve the goals on which they are based on the then they would automatically become true. They also introduce the notion of time initial literals. These are literals which become true at certain points of time, pre-decided points of times, and become false at certain points of time. So, for example, night and day, every day in the morning the sun rises and every day in the evening the sun sets, and we can model things like exogenous events. So, if you are planning an outing, you may have to take into account the fact that you want to do it only during daylight. Then in PDDL 3.0 they introduced state trajectory constraints. We have spoken about that not only are we interested in what is true in the final state, but also what is true along the path that took us to the final state. We also added preferences or soft constraints that we have spoken about, that goals which do not necessarily have to be achieved, but they are desirable, they are preferred, it is preferred that you will achieve those goals. And then we introduce object fluents, that if you have functions inside your language, then the function could not return just values, for example, how much petrol you have consumed, but also certain objects as to what is the object that you have bought, for example. We will confine ourselves to the strips domain, as I have been repeatedly saying, and we will take a break at this point and come back in the next session and start by describing the strips domain and the problems we can solve in that. So, see you in the next session.